Hi, hello everybody. So this is the video dealing with section 5.3, double angles and half angle formulas, and this is the first part where we cover double angle formulas. Um, so these formulas, so we'll see, the double angle formulas, the half angle formulas, and there's some other formulas that we have seen before in different sections. They're all used for several reasons. So the main reason here is that they help to simplify all sorts of kind of trigonometric expressions that we may have. And these expressions may be inside trigonometric equations or just to evaluate trigonometric functions. And if you have to take, calculus courses, you see that they're incredibly useful in simplifying, complicated expressions dealing possibly with integrals and other functions. Okay, so at first they seem to not be very useful. It's because we're just learning how to work with them without any context. And obviously, in this course, it's a pre-calculus course, so we're going to just to show you how they're useful. But the real benefit comes when we have application problems. Okay, so these are just some of the things that we can do. Um, But let's just see how they work in practical sense. Now, so first we're going to take care of, like I said, so this part is the double angle formulas, and in the next one we'll see the half angle formulas, the next part. Okay, so the very first thing that we have to mention is sine 2 theta, cosine 2 theta, tangent 2 theta. Okay, their definitions are here, but it's very important that you understand the following. Sine 2 theta, this is not like you're adding, for example, x plus x and you get 2x, right? So sine 2 theta is not 2 times sine of theta in case of the x plus x. So this is an angle, right? And this is 2 times a function. So two different things. And the same is true for sine, cosine, and tangent. So don't make this mistake. And later, in a separate video or in a separate section of the course, we'll talk about sine square theta, okay? And I think I've mentioned that before in a separate video, that sine square theta is sine of theta times sine of theta. So this is the function square, and this is not the same as sine of theta square, which is the angle square. All right, so don't confuse those two things. It's very common, and this comes from the book itself because it's such a common mistake that students make. And here's an example for you to see that it's not the same sine 2x, not the same as 2 sine x. So if we let, for example, the angle be 30 degrees, so sine of 2 times 30 degrees is sine of 60, which is radical 3 over 2, which is not equal to 2 sine of 30, because sine of 30 is 1 half. So 2 times 1 half is 1. Right? So definitely not the same. So do not make that mistake. Okay, so the examples that we have to cover in this section are extremely easy. It's just an application of the formula itself so that we can evaluate an expression. All right, so let's see the couple examples that I have here for us. And I'm going to leave it here so that we can see the formulas. Now, in these problems, so notice that the formulas themselves do not mention anything about where the angle is located, along the unit circle, right? So we don't know if the angle is in the first quadrant, second, third, or fourth. So the problem would have to tell us. And we need to know if the angle on that particular quadrant has a sine, cosine, or tangent, positive or negative. Okay, it's not that hard, and I'll give you two ways to do it. Okay, so let's take a look at example one, sine of 2 theta. So the formula that we have to use is obviously that one. We are told that sine of theta is 5 over 13 and that the angle is in the second quadrant. Now, so let's recap, right? So this is y, which is our sine of x, and this is x, which is cosine of x. If the angle is in the second quadrant, that means that the angle is here. Okay, here I have this is the sine right here. This length is the sine. Now, obviously, above the origin, this is a positive y coordinate, so the sine is positive. Okay, and cosine is this segment right here on along the x-axis, which is negative. So this is how you can tell if sine is cosine is positive on a particular quadrant. Now, if you don't know or you don't want to do it that way, here is a shortcut for you to know using the calculator, since the calculator will be allowed on exams. So an angle in the second quadrant would be something over 90 degrees, less than 180 degrees. So let's say I have 100 degrees. This is definitely in the second quadrant. So this is what you can do. Pick an angle in that particular quadrant, go to the calculator, okay? And if you're interested in sine, use the sine function, pick an angle on that particular quadrant. And obviously, we're not interested in the numerical answer. We're just interested in the sign, right? Positive or negative. So this is clearly positive. And if you wanted to confirm that cosine on the second quadrant is negative, type an angle in the second quadrant, and you see here's the negative sign. So it's very easy to find out if an angle is positive or negative for a particular function in whatever quadrant you're working with. You can do that. But I usually will use the unit circle because it's useful information. Okay, so knowing that sine is 5 over 13, I have to find sine of 2 theta. So I'm going to use this function or this equation. So sine of 2 theta equals 2 sine theta times cosine theta. Now, I know what sine is. Obviously, I know what 2 is. I know what this is. I need to know what cosine is. All right, so I go to the unit circle again, and I am told that sine is 5. You don't need the unit circle. In fact, I think I'm going to do a better job and just show you the triangle. Okay, so here's an angle, maybe the reference angle, because obviously this theta is in the second quadrant, but here's a reference angle, and I was told the sine is 5 over 13. Now, we know that sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So I need to find this x from this triangle. Well, obviously, we can use the Pythagorean theorem, which is 13 square, 5 square, and x squared. So 13 squared, 169, x squared, 25. So subtract 25 from both sides. And I have that 144 is x squared. Take the square root of both sides. And we have that x is 12. All right. So my cosine, now this is important. Cosine from the basic definitions of the trigonometric functions is the adjacent side of this triangle, which is 12 over hypotenuse. Now, here is where you have to be careful. This is the numerical value of cosine, but cosine is in the second quadrant. So go back to our picture here, or go back to the calculator, pick an angle in the second quadrant, and determine if it's positive or negative. It is negative. We saw it because I already tried the cosine of 100 degrees. So this value here, you have to attach the minus after, okay? So the cosine of an angle in the second quadrant is negative. So now that we know sine and cosine, we can use this formula. So 2 times 5 over 13, negative 12 over 13, and that is equal to 10 times negative 12, and then 13 times 13, 169. And then I guess you can simplify this if you wanted to. I'm going to do that right now. So 120 over 169 and approximately 0.7100. Okay, so this will be minus 0.7100. All right, so this is sine of 2 theta. All right, let's do the other one, cosine of 2 theta. And then this is where, again, you have to be careful. We mentioned that all of these, right? Erase this. If you want, you can always stop the video. Remember, right, all this, right? So don't think it's 2 times cosine. So we use the formula for cosine now, and for cosine we have, a couple of different choices. We have the basic definition or identity, and then we have the other two. They're all the same, but sometimes one may be better than the other. I think in this case, we can use the basic one. So I'm going to say that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. But you can use the other one as well. For example, you could use this one, 2 cosine theta minus 1. I already know what cosine theta is. We calculated here before. That was negative 12 over 13. So I'm not going to do it again. It's from the triangle. Now, so remember what I said a few minutes ago, that cosine squared theta is not the same as cosine of theta squared. This is angle squared. Cosine squared theta is cosine of theta times cosine of theta. Okay? So this is 2 times cosine of theta times cosine of theta minus 1. So I have to do that first. So this is negative 12 over 13. Negative 12 over 13 minus 1. So this is 144. 2 times 144, 288 over 13 squared, 169 minus 1. And then we can do this on the calculator. I mean, we don't need to have the answer in fractional form. So we can go to the calculator right now. So 288 divided by 169 and then minus 1. And 0.7041. And that's our answer. Okay. All right, so this is cosine of 2 theta, just an application of the identity, nothing more at this level. And let's do and you could check if you wanted to, that this would give you the same result. In this case, possibly this was the easier one, but you could have used the other one as well. So tangent 2 theta. Okay, so tangent 2 theta, I'm going to use this identity. So tangent 2 theta equals 2 times tangent theta 1 minus tangent squared theta. All right, so 2 times tangent theta. So what is tangent of theta? Well, tangent from the basic identity definitions is, as you know, sine of theta, cosine of theta. Now I know what sine is 5 over 13. I also know what cosine was, which was negative 12 over 13. Okay? And then we multiply by the reciprocal and we get, so the 13's cancel, and we get negative 5 over 12. So that's my tangent for our angle in the second quadrant. So you know, if sine is positive and cosine is negative, obviously positive divided by negative is a negative for tangent. All right, so 2 times tangent of theta, which is negative 5 over 12. 1 minus, again, tangent squared theta is tangent of theta, right? So this is your negative 5 over 12, negative 5 over 12. Now this is, so the numerator is negative 10 over 12. This part is 25 over 144. All right. So I'm going to write here 1 minus 25, 144. Now, again, you do not need to evaluate this using fractions. You just don't have to. All right. You can use the calculator and evaluate this whole thing. So I'm going to do exactly that just to show you that this is perfectly fine. The answer that we want here is a decimal, not necessarily a fraction. It doesn't matter to me. All right, so let's go to the calculator. So I'm going to do first negative 10 over 12. So 10 divided by 12, and I'm going to give it to you as a decimal instead of as a fraction like you would in a, basically algebra course. So I'm going to say 0.833. 0.833. Okay, 3 decimals is fine. And let's do the denominator, which is 1 minus 25 divided by 144. And that is 0.8263. Okay, 0.8263. And we divide one by the other. So 0.8333 divided by 0.8263, just about 1.00. That's approximately 1. All right. 1 point, if you wanted to do more decimals, right? 0084. All right, there's no need. So approximately 1. Okay, so this is how you can apply the double angle formulas. Now, before we finish this video, I wanted to show you one particular problem that comes up quite frequently. And this is, like I said, this is for a maybe more advanced application where we would benefit from using these, in this particular case, the double angle formulas, but the same applies for the sum formula, the product formula, the half angle formula, and so on and so forth. Now, this may come up in calculus, for example, or more advanced applications where you are given an expression and we have to find the exact value. Now, when you see the expression exact value, what we mean is you cannot use a calculator for it. So we need to find the answer in terms of radicals. Okay? So this is a complicated expression. 2 tangent 15 degrees minus 1 tangent square of 15 degrees. Now, the angles that we have to know are here: 0, 30, 45, 60, 90, 180, and 270. Okay? Obviously, the 360 is the 0. So we are going to look at let's make it a little bit smaller. We're going to look at the tangent identity, and we're going to see if we can apply it here. Okay, so let me just erase this part. All right, so 2 tangent 15, 1 minus tangent square of 15 degrees. So here is the identity for tangent to theta. 2 tangent theta over 1 minus tangent square theta. And look what I have here. I have here a 15 degrees. So my theta is 15 degrees, right? It matches perfectly. 2 times tangent 15, 1 minus tangent square of 15. So theta is 15. So which means that this expression is equal to tangent of 2 times 15 degrees. Well, 2 times 15 degrees is 30 degrees. Now, this is one of the angles that we're supposed to know. So I go here to 30 degrees, I check tangent, and I get this value. So this is tangent of 30 degrees, which is exactly radical 3 over 3. So this is what we meant by several times of applications, where to work with this expression here is incredibly complicated. But as it turns out, that this complicated expression is nothing more than radical 3 over 3. So there are tremendous applications for these trigonometric identities, in this case, the half angle or double angle in this section 5.3, that we can apply, not only to simplify expressions, solve equations, and as you see here, maybe in some more advanced calculus problems.